For those of you who don't know me, my name is Tarana Solati. I'm the Associate Dean of Research and Innovation in the Faculty of Forestry. And it's my great pleasure to welcome all of you to another research seminar in our faculty. Before I start, I would like to acknowledge that UBC's Point Grey campus is located on the traditional, ancestral, and unceded territory of the Musqueam people. This land has always been a place of learning for the Musqueam people, who for thousands of years have passed on their culture, history, and traditions from one generation to the next on this land. We are very grateful to live, learn, and do our research on this land. I also would like to thank some people before we start, Frederick and Luis, for setting up the AV systems. I would like to thank Sonia and Jillian for preparing the poster, the seminar poster, and also I'm thankful to Karim for sending all the emails about this meeting. Now let's introduce Dr. Chomping Dai. It's my pleasure to introduce Dr. Dai. Dr. Dai is an associate professor in the Department of Food Science in the Faculty of Forestry. He leads the Bamboo Applications and Manufacturing Lab, focusing on the development of bamboo and wood composite materials for sustainable building and packaging applications. Before joining UBC, Dr. Dai was a principal scientist at FP Innovations and also an adjunct professor at UBC in the Department of Wood Science. He is a fellow of the International Academy of Wood Science, known for his work in developing mathematical models for wood composites. Having authored close to 300 technical publications and supervised over 30 HQP, he brings extensive research experience in manufacturing wood and bamboo products. Please join me in welcoming Dr. Dai.
Thank you very much, Marilyn, and thank you all for coming to the seminar. I was worried that this is the off season, so I had to make it like a lot of people that I met is Kim Holden. Make sure that I mean, so it actually worked. Actually, how many of you had experience in with bamboo, whether you've been to a bamboo field or factory or a garden?
Using chopsticks doesn't.
How many of you actually grown up in bamboo garden in your field, in your yard? Quite a few. Okay, thank you. And you know what? I'm one of those. Actually, growing up in a remote area of China, we had in a village. We don't have much actually. This is we're talking about 50 years ago. There was no television, there's no car, no highways, and so really having a bamboo garden or bamboo field in your yard is really something of luxury because you can get a lot of stuff from the yard. So needless to say that, you know, for me as a researcher on bamboo, I have an affection on bamboo because where I come from. And really, if you have a chance to actually, you know, walk in the bamboo field and make the connection with bamboo, and I'll bet you all will have me and like what bamboo brings. So for me, growing up again, and I was very fond of fishing. The tools that I have are made of bamboo, whether it's bamboo trap or fish rod or a net even. So, and also the household items like basket and ladders and even the hangers made of bamboo, and furniture, of course. And my favorite thing about bamboo is bamboo shoes, actually. Any of you tasted bamboo shoes? Yes. Yeah. You know, I think the best flavor of bamboo shoes is actually cooked with like a meat, like a pork or something. I highly recommend it. I don't know if you can find that in Vancouver, but it's delicious. So bamboo becomes the kind of a personal thing for me, but also in the Chinese culture, going back to over 1,000 years, even more. Some of the famous scholars actually wrote poem and famous things about bamboo. So what this saying is, this is from sushi. If you're Chinese, everybody knows who sushi is. If you don't know, and then you're man, I guess. Very famous poem. That's in the Song Dynasty. And he wrote a long poem, and this is just a couple of sentences. What it says is that 食无宁可食无肉，不可居无竹。竹 is bamboo. And so what it says is that if I translate directly, it says food cannot go without meat, or can go without meat, but living cannot go on without bamboo. But I guess, you know, my poor translation is that what he's saying is that I can live without meat, but not without bamboo. So that is kind of incredible. And this is from a very famous poem and a scholar in Chinese history. So obviously bamboo brings a lot of characters like strength, resilience, and persistence. And then speaking of that, I'd like to bring the character of my group. And I had the very fortune to bring together a group of young scientists and students over the last few years, and they made a lot of contribution to my research, particularly in the area of bamboo. So I want to thank them for that. Some of them are here, and some of them actually graduated already. So I'm gonna just today talk about their research. I'm not gonna go through the details now, but yeah, and I also missed some of the visiting scholars that we had over the years. So what I'm gonna talk about today is focus on bamboo and what makes bamboo so interesting and unique. And particularly, and everybody knows about how fast growing bamboo is. And how, why, how does it compare with on tree, right? And then some of the properties, carbon sequestration potentials, and also the material properties. Because for us, we're most interested in using bamboo as a materials. And then we're going to focus on some of the product that we've been looking at, developing from bamboo. And then focusing on manufacturing technologies, which is kind of dear to my heart. And then looking at what might be the challenge ahead and the solution for bamboo development. So bamboo as a resource is mostly native to the southern part of the world, and where the climate is more kind of warm and humid. There's over 1,300 species, might be closing to 1,400. Most of them are along the Pacific, Asia Pacific, America, and South America, and Central America, and Africa. Now there's actually more interest now in Europe and the United States growing bamboo already. So you may wonder, can we find bamboo in Vancouver? Um, So this is actually bamboo garden. I don't know if you've been to the cake house in downtown. It's kind of expensive. I haven't been there. I've never been there. I just sneakily go there and my wife take a photo of it. She actually used one of those beautified lens or whatever. Maybe look better, but the beauty of bamboo garden is real. And this is also real in Burnaby. I didn't realize this until when we had the conference, when we held the engineer bamboo conference, and one of the electrical fuller, he told me about this, and I checked it out. And it's amazing, like how big bamboo can grow in climate like Vancouver. So I'm going to talk about a project that we actually take advantage of for large size bamboo that we can find in the region, how that might complement the product that we have in Canada, which is engineered wood product. So the first thing about bamboo growth, everybody knows how fast bamboo grows. Generally, there's a common saying like bamboo could grow like as fast as 1 meter a day. If you look at this real data, and you can see it takes a little bit in the beginning, but when it reaches to this like a second week or third week, and there's a period, bamboo just shoots up, reach to its maximum height, before kind of level off. It takes less than a year, basically less like just a few months before bamboo reach to the maturity height. And then it started grow in terms of lignification, so the tissue become harder after that. So what makes bamboo grow so fast is that bamboo has knots, right? Nodes. So normally, if you look at wood, right, what makes wood or tree grow is the sort of the meristem at the top, just at the very top. And then if you look at bamboo, there's meristem at each bottom of the node. So bamboo, when it grows like simultaneously at each node. So that makes bamboo grow so fast in terms of this, the cells. But also what's interesting about bamboo is that bamboo, the nutrients of bamboo is supplied not just about the roots or the rhizome we call it, by the single bamboo itself, but also the surrounding the bamboo. They're all connected underground. And there's a period of about 8 months that bamboo start to like grow, and it's like pregnancy. What, 10 months pregnancy for humans? It's 9. I thought it's 10 years, but no, it's 9. It's 8 to 9 months for bamboo. It actually grows underground. So before the shoots goes up, that's when it starts really to pick up. Okay, so it's very interesting that way. And then if you look at tree, on the other hand, it grow only up from the top. And then of course, tree has the secondary growth or the diameter growth that bamboo does not have. So when bamboo shoots up, the dimension or the diameter of the bamboo is actually already set. Okay, so it actually pops up every node in high direction. So that's kind of more or less hopefully answer the question of history of bamboo, how fast it grows. And of course, when it comes to materials, we're not just concerned about the height, but also the biomass. And then this is the scale of a Chinese fir. The reason I choose Chinese fir is that it's the same climate with which the bamboo grows. So that's kind of an apple to apple comparison. And so we're talking about the time scale of 20, up to 20 years. Obviously, this is a fast growing species in terms of wood. But if you compare that, bamboo mature time is like 3 to 5 years. So almost we're talking about like 10 times in terms of location for wood. So when it compares the biomass growth, so the amount of the tonnage of biomass over a given area and over a year, and we compare that, and bamboo is at the top. Following that is the southern yellow pine, as you know, like it's so common in United States, US, southern US. And then you got the teak, which is very typical hardwood that you can find in tropical area, very dense. Teak density is actually equivalent to bamboo. And then there's our Douglas fir. For Douglas fir, I mean, it grows so slow. Right? That's part of the reason that driving our, industry to the south, because we not compete with the fast-growing species like the southern yellow pine. But then I didn't list the eucalyptus, what you can find in Brazil, which is even like faster. Okay. So bamboo has a, both the ability to grow at the dimension of like height direction, but also the biomass. So one of the things also about the carbon capturing, again, we're comparing bamboo with Chinese fir. You can see the fir is the rotation, let's say it's about 35 years. After that, you get cut, and then you grow the tree back again. So this is a real study. And then you look at the carbon accumulation for bamboo. It just shoots up. Note that we have these steps. So each step represents like 5 years of harvesting. And what's magic about bamboo is that when you harvest or cut bamboo, the rhizome actually stay alive. It does not die. Okay. And then whereas when we fall a tree, the roots start to erode. And so you emit right away, you start to emit carbon dioxide. So that's the main difference. And also the other difference is obviously how fast it grows. And of course, the amount of underground biomass is substantial. So because the fact that the bamboo does not die, the plants stay alive after cutting, makes bamboo kind of a cumulative during the whole rotation or harvesting process. So before I get into the material side, I want to mention that the study that we also do in the area of societal and the environmental and societal impact. And I have a close student with John Ennis. We're looking at beyond sort of the technical material manufacturing side, but also social impact. And she's in her 4th year, and she's going to graduate. With that study, she does a lot of the interviews and talk to various people in terms of the strengths and opportunities, weaknesses and threats of bamboo industrialization. So back to the material, the product side, which we'll be focusing on. This is a bit complicated. Sorry about that, but if you look at bamboo, you got the bulk structured bamboo, which has the comb, you got the diaphragm, and you got the nodes there. But by and large, you got the outer skin and inner skin. The majority material of the tissue bamboo is made of what we call the fiber bundles in darker color, and the lighter color is parenchyma cells. So if you look closely, the fiber are more kind of a straight, continuous, whereas the parenchyma cells are kind of short and thin in terms of cell wall and cell structure. And then you're going down to the cell itself, and the number of layers is actually quite different, and the structure of layers is quite different from wood. And it has multi layers and up to like 8 or 10 layers, whereas wood you got S1, S2, and 3. And it's also up to 3 layers. And then the microfiber angle is the same thing. We bring it down further. You got the chemical composition, which is cellulose and hemicellulose and lignin, and which is more similar to a hardwood than softwood. But in a layman's term, in terms of the bamboo structure, though, when it comes to properties, we consider bamboo as a naturally optimized composite product material, where you got the soft tissues, parenchyma cells acting like a sponge. And then you got the continuous fiber. This is actually real. Somebody did the study in University of Maryland. And when he actually dissolved the bamboo by removing all the lignin and hemicellulose and able to actually get continuous macrofiber. You cannot do that with wood without dissolving the whole thing. So that just shows that bamboo, the fiber is really like a straight and well connected. And that continuous fiber plus the soft matrix makes bamboo strong, but also flexible. So if we, when it comes to engineering properties, and when it comes to, let's say, building applications, we're concerned most about the strengths and then the elasticity. We do a simple bending test, like apply load and see how much load it can uptake and then how soft and how rigid materials in terms of elasticity. You can see bamboo is actually going higher into a maximum load, but mostly it goes through a longer deformation process before it fails. Whereas wood is more rigid and brittle. And what that means is that the strength of bamboo is much higher than wood. On the other hand, that's because the fiber and how straight the fiber is and how continuous the fiber are. But also on the other hand, the elasticity, which is also important for engineering application, is actually lower, relatively lower, which is actually interesting because for most engineering materials, you usually have high strength and high elasticity. But in bamboo, you have higher strength compared to wood, or relatively lower in modulus elasticity. That is because the unique combination of the soft matrix, the tissue and width and the fibers. So using that ideas, I was fortunate to be involved in a development project where bamboo is used as the fiber, and then the fiber is made into curtain and rolled up to a pipe. But that is because the bamboo fiber is so easy to roll and be flexible, but yet the bamboo fiber is much stronger. So that is kind of a perfect application for product like bamboo piping. This project has gained commercial success already. in China where it can be used for sewage pipe and drinking water pipe, and even utility tunnel. And as you know, like the utility tunnel can be very big, as big as like 5 meters in diameter. So this is kind of the example how bamboo materials being utilized and also utilized to make more sustainable products for infrastructure applications. And even this example of the bamboo pipe being kind of modified into more kind of a square shape. And then it can be used as a unit to build houses. And also can be rolled into such a continuous fashion that can be used to make bullet trains. Not commercialized yet, but nevertheless, it's a great idea. Another product that we being involved in utilizing from the big end to the smaller end is using bamboo fiber. And bamboo has, by the way, been used intensively in China for making pulp, for making papers. But here there's a growing interest in using bamboo fiber as a raw material to make boxes, food packaging to replace plastics. There's actually there's a big kind of a movement in China right now that they're using bamboo as substitute for plastics. As you can imagine, there's a great potential there. So the idea is kind of simple. When it comes to food packaging, takeout food packaging, you use it for like 30 minutes and you throw it away. So really you try to find the cheapest or most renewable fiber as possible. So the template there is, instead of using wood, you use like an annual waste fiber like grass or like straw. And then there's inherent deficiency in these fibers compared to bamboo. So bamboo becomes an enhancer for these materials. And then of course you add some additive for performance. So you can see bamboo, the fiber is much longer and the coarseness is actually is lower. Coarseness is the thickness of the cell, which is thinner. So the thinner wall actually, when it comes to making these products, and you can increase the bonding, you can easily collapse them and increase the bonding or the performance. And the longer fiber actually help to create more network and stress transfer for the performance of the product. So in both cases, bamboo has advantage. So we were able to make progress in actually not only make the product and compare against the existing product, but also we've done quite a bit of work on the degradability, biodegradability. And one of the key things that we try to address is the chemical PFAS chemicals or forever chemical that's used to prevent water and oil penetration. No, we've made product that without using those forever chemicals, and that's the performance really well. And that's actually Cam having show off on her project, but she's too shy and you have to use the product to cover herself. Great job there, Cam. You know, you did really well. The other kind of exploratory work we've been doing is try to take advantage of bamboo as a unique fiber that has a very high surface area and a very high porosity compared to wood. The porosity is usually about, let's say, 50% higher. Specific surface area could be 2 to 3 times higher than wood. So bamboo has known for its ability for purification application. In age where we're talking about how to purify air or purify water, bamboo can play a major role there. And so we've done some work, and I've done this with collaboration with our colleagues in Zhejiang Agriculture and Forestry University. They've made this very good progress there. So much about all the various applications of bamboo, but indeed bamboo, has this ability to be used as a material to make many products because it's a unique structure and material properties. But for us, in this part of the world, like we're more accustomed to like buildings, houses, with big volume, and because all the other stuff is kind of a small in quantity. But those other application has higher unique price, more expensive. But if you look at building material, there's a huge market out there in terms of volume. So our focus and why we're doing this has been trying to see how we can actually use bamboo as a building materials, how it can be used as a complement for wood products. So we've been actually looking at building our capacity here in UBC in the COP Center, and we try to develop a forming rig system there. We can handle all the bamboo strips and then apply load, and then we can apply resin in a more semi-automatic way or controlled way, and then can feed that into a press that we have in the COP. And we can successfully make small billets like this and test them. One of my students, Saul Rodriguez, has made a very big progress there. And Eric is another student that he just finished his work, and where we combine bamboo with different processed bamboo with wood. In the core here is just a LSL, or like an equivalent to OSB, laminated strand lumber, and then we laminate it with different type of bamboo, and we can significantly upgrade the strength of the product. And by the way, these are the local bamboo species that we harvest and made. And you may think this improvement is trivial, but it's not, because if you look at the wood products, like PSL is at the top of the range, and LSL, OSL, a company like major producers, they can only make to this level. So if you can just bring it up, that means huge in terms of their market opportunities. And Bamcor is one of the companies in the US actually successfully use bamboo as a building materials. So we kind of compare against their product. And so we essentially develop a product that is cheaper and stronger, and also can help the Canadian composite lumber producer to meet their market requirement using locally grown bamboos. So focusing on a little bit more very quickly, the unit bamboo products. Again, bamboo can be easily used in a similar fashion, whether it's like composite lumber or even mass timber. But if you look at the process of bamboo, though, it's quite complex, more complex than wood, for the fact that bamboo is a hollow structure. You have to deal with the hollowness, and also you have to somehow overcome the skin, which is generally the phase for bonding. Skin cannot be used for direct glue application bonding, so you have to somehow deal with that. So there's definitely various way of removing the skin or modify skin, at the same time try to control the geometry of the element, and also try to maximize the recovery. So basically boil down to 4 types of products. the laminated one that's common has the lowest density, but the recovery is low. Because you gotta get the square out of a round shape. And then you start to look at actually unfolding bamboo. I'm actually holding a piece of bamboo here. What they're actually doing is that they try to unfold this and make it this flat, like a veneer. So that way it can significantly improve the recovery. And further, if you kind of screen them and keep the skin, and then your recovery utilization can get in. So when it comes to further processing, bamboo has its obstacles compared to wood. This is actually direct comparison on the same scale. You can see how large the pits are for wood. It's about 7 times bigger than a simple pit that you would commonly find with bamboo or wood itself. So that actually makes bamboo material really difficult to dry. And also difficult in terms of glue penetration. You can see from this example, on top is the wood, the bottom is bamboo. The same glue applied, the PF glue applied, you can see how glue can easily migrate from the surface, the interface to the inner cell, whereas almost nothing can go through bamboo. So there's real requirement in terms of the treatment of bamboo and how the glue is applied. We've worked on this and proposed a new method where we need to apply glue to 2 different glues to the bamboo and to wood separately. Therefore, when it comes together, we can actually maximize or improve the bond. This is what we call a dual glue application system. And the other hurdle with bamboo is the drying, like I said, because the low permeability, it takes much longer to dry. It's hard to believe that simple strips like bamboo takes even longer time for us to dry than a 2x4. 7 days. So one of the reasons Monica did the study is that it's again to do with the low permeability, but also the soft tissues. Remember the sponge? It tends to actually collapse when you dry. Mind you, like during drying, we also have to go through a carbonization or caramelization process. The bamboo tissue is heat treated to make it more mold resistant. Mold is common in bamboo because it contains starch, like you see in this. And then that has to be treated or removed and heat treated, and then you along with drying. So at some stage during the drying, primary drying stage, the water is removed and you create a vacuum basically because it's so small. The vacuum pressure is too high for the cell to hold and the cell start to cloud. And then you gotta go through a secondary steaming process to recover the cells. And because of the mold issues, most of the bamboo process has to be built up in terms of what we call a kind of a satellite manufacturing model, where the bamboo has to be harvested and processed right away. The primary process allows bamboo to be dried to get into a more kind of a handleable form, and then the semi-processed bamboo lamina can be sent to a larger mills for packaging. And looking at the engineered bamboo, really, if you look at the strips, it's pretty much similar to what we see in parallel manufacturing process. But the process is so manual, you can see that the operator is there kind of hand forming them. And there's a lot of variation. So Hugo did a PhD to simulate this and found there's a lot of variation. And he kind of predicted how one should be densify the product to achieve the optimal performance yet getting the maximum volumetric. So with that, we're proposing more kind of a layered system instead of a random material structure to allow the maximum recovery and optimal performance. On the pressing side, just this will last a bit. So when it comes to manufacturing engineered bamboo product, pressing is critical because bamboo is so hard. It requires a lot of pressure. In the first version of bamboo spimber or the hard bamboo floor that you see, they actually made with very little size. Like you can see the size is very narrow, although it's a bit long. But because the pressure that requires is so high, so then there's a second generation of manufacturing process, the heat is introduced. And that allows you to make like a more kind of panelized product. And then allowing heat to help with the consolidation. And in that process, the hot pressing is like a real problem because it takes so long. And this is looking at the pressure, how the gas pressure is building up inside the product. And you have to release that pressure before you open it. Otherwise, you're gonna have the blow or the delamination. So that process takes over an hour, which is really a problem when it comes to litigation and in terms of cost. So what we're looking at in the future, we believe that the bamboo can make a huge stride in terms of its production efficiency and performance of the product by adopting the parallel model, where density is lower, therefore permeability is higher, and the forming is going to be more automated instead of a manual. And most of all is the pressing. Like you see how fast the parallel is pressed. It's mind-boggling. It's like within 2 minutes compared to an hour or more than an hour, right? So there's a huge opportunity there for bamboo to benefit by developing that technology. And also, and another way to also improve the automation and manufacturing process is by looking at the OSB example, because then you can strain bamboo with the skin on. And we've actually started to work on this with our collaborator, Katie Kamana. They're a global supplier of OSB strander. We just finished that work, and there's a growing interest in using bamboo as a feedstock for OSB. I'm looking at the time, so with that, I'm going to just stop here by saying that bamboo is really a wonder plant that presents a lot of positive attributes and both economical, social, environmental benefit to mankind. And however, there's a lot of work to be done to actually realize that. Thank you for your attention, and thanks also to our sponsors. If you have any questions.
Any questions for Chauncey?
Thank you very much for the impressive talk. I have one small question regarding the underground living part you mentioned. How do you actually measure living part is actually 40%? How do you make sure it was that number?
That 40% is really a very gross estimate. It really depends on bamboo species. Like I said, there's over like 1,300 bamboo species. Some of the bamboo species like are very small. So the amount of underground is gonna be like way higher. It's probably 100%. Okay, and then for larger bamboo, the number is gonna be lower. But I didn't do studies. There's a ton of studies being done actually. Okay. And we actually did a bit, we did the off, like a top, we cut some bamboo, which is where the biomass. The underground is kind of more difficult because they're all connected. There's a lot of work being done, you know, and to sort out, you know, the rhizome, the roots, how much it accounts compared to the underground biomass.
Other questions?
Thanks for the talk, Xiangping. So just thinking a bit about your comment about the drying and just how challenging that is relative to normal wood. And then I was thinking about the gluing and I was thinking, is there some way of kind of combining the gluing process? In other words, use a latex-based or a water-based glue and the drying somehow at the same time as a way to kind of, maybe it takes longer to cure, but maybe less energy. Just an idea that came up and I was just kind of curious whether you, further reflections on the drying and the glue.
Yeah, that's definitely thinking outside the box, you know, like usually the way it goes is that, you know, like you dry it and you remove the skin and then you start to apply glue, and then the glue only works when the moisture content is below usually 4%, you know. But if you look at the bamboo scrimber, the way it works is that they actually scratch the surface and actually crush the bamboo strips and to break up the bamboo surface, and they actually dig the bamboo strip into a solution so they semi-impregnate the bamboo strips, and then they dry. So there is that process there. They combine lamination and drying in the case of bamboo timber. But I hear what you're saying, like basically you're saying like forget about the initial drying, primary drying. Let's go with the bamboo in its wet stage, and then that's a pretty good idea. Maybe it should be explored. Maybe.
Paralam already does that. You take wood strands, you dip them in resin, and then you press it into a board. So that's already been done. The difference between scrimber and Paralam is there's a huge difference in resin content, whereas scrimber has like 15% PF solids by resin. Paralam is quite a bit less. It's like 3-4% maybe.
What about like latex glues, like water-based glue? Does that get used in Paralam?
Not for anything structural.
Well, you know what, Richard, we're gonna look into that. I think it might be possible there, because drying is real issue.
When you were talking about the benefits of bamboo, the strength, flexibility, and then you showed products are actually commercialized in China, some like for piping and then the cube one for housing. How about the structural wood material that you showed? Are there any commercialization of that here in Canada or somewhere?
Yes, yes, actually, there has been some buildings built with bamboo. And currently, it's the laminated bamboo has been used, the lighter weight, not the heavy ones. It's been used as a project. As a matter of fact, there's a hotel, a famous hotel, Jakarta, in Amsterdam, actually made with all the engineered bamboo products. So there's been a successful example already, but it's just the cost. And then the heavy duty bamboo scrimber, it has been used already widely for outdoor, like the siding product for buildings, or even for bridges and so on and so forth already. But those are very expensive products.
Yes. Okay, thanks for Professor that give us a great presentation, and I have 2 questions for this. The first is, what is, in your opinion, what is the outlook for bamboo-based engineering materials? And what is the biggest challenge for bamboo when bamboo using in construction? Yeah, the second one is that Yeah, you have been to the bamboo forest in China and in Vancouver, especially the Burnaby. Yeah. And what is the difference between the bamboo in China and in Vancouver? Thanks.
Okay, thank you, Professor Liu. I'll answer the second question first. And basically, what is the difference between the bamboo we found here? They're big, what I call it, but they're not as big, first of all, as most of that you would find in China. Although it's a similar species, it's a similar species that those big one in Burnaby. They actually also the wall is actually thinner. It's not as thick. So, and then the density is higher. But one of the amazing attributes for the species that bamboo we find here is actually stronger. It probably grow like in a colder climate and make the tissue grow slow or something, and make it stronger. And then the second question about the engineered bamboo for construction. Yes, there are examples being used. And now there's a lot of effort there, first of all, to establish the code, international codes for building codes for using bamboo. And also, one of the key challenges is actually the durability, the mold resistant. And of course, like I say, the biggest challenge is the cost. And I believe it still costs more. So you gotta make it comparable with the engineered wood. So to reduce the cost, it has a bit of a long way to go. Like I said, you gotta go with a smaller, like a larger scale or more automated process, like we do here in processing of pellet.
Okay, thank you. And do you have some suggestions for?
Let others also
Yes.
ask questions. There was one question here.
Professor, thanks for the presentation. So as far as I know, and also probably you know that in my research, I used bamboo scraper and also laminated bamboo format tests. So these are two major engineered bamboo products started in my program. And with the issues that you mentioned in your presentation, so the founding and the drying process, I wonder, with your solutions, will that largely change how the cost of the products, or will that like are they like targeting and makes them like be more compatible with engineered wood products?
Yeah, the product you use for connectors, and those are heavy, like denser ones.
Yeah.
What I'm proposing in terms of performance, it won't affect the laminated product, but it would affect the scrimber, like the heavier one. Because I basically propose lower density.
Yeah, right, exactly.
Yeah, so it probably won't be looking at the product for connecting. And but for you're looking at the connector, which is really requiring as strong as possible material. So I don't think you need to worry about, using a more kind of commodity engineered bamboo product.
Will the change of the process, the gluing process, will that change the mechanical properties?
Not really.
Right, it's just the cost of the whole
Yes.
thing.
Yeah.
So the follow-up will be like, how feasible is that to change, to use the manufacturing in PC in the wood industry, like ask them to change their raw material to bamboo, like how feasible is for them to use both materials in the same settings?
Yeah, we'll basically try to modernize the process. Combining that.
And here, and I think that's the last one. We have one more there, and that would be the last one.
Our action point of view, using the to achieve a zero carbon or not to other.
Yeah, I think so. In terms of carbon sequestration and carbon capturing for the product, bamboo definitely has advantage as the raw material, but it has a bit of a disadvantage at the moment in terms of processing. But the net part, I would say there's potential for it to be a negative. Yes.
Hi, Dr. Thank you for the presentation. So I have one question about, again, you mentioned durability is quite a critical for the bamboo building application, for example, right? So can you comment on what are the current treatment technology used? Because I noticed that you also mentioned, seems like for adhesive, it's difficult to penetrate into bamboo surface. So for treatment, I guess, must be some different technology used for bamboo.
Yeah.
Can you comment on that?
Yeah. And there's two ways of looking at it. One is the heat treatment. Right now, the outdoor application, they're really just heat treated. Yeah. And also there's a way of using preservative treatment as well.
Thank you, everyone, for attending our research seminar series. We will not have any more research seminar this term until September. So please enjoy your time for the summer, and we will see you in the new term. Thank you.